I'm always really bad with names at the very beginning. And it slowly improves over time. Okay, audio is working. Okay, let's see the video participants. Share. Okay, time to start. Okay, so where we were, I better stop the music. I'm not going to try to compete with music. Okay, so here's where we were last time. We were talking about partial derivatives. Let me just remind you of how that works. We're going to pretend everything's constant except for one variable. In other words, we're going to take our multivariable function and pretend that it's a single variable function, right? Very, very sort of, weak first attempt at differentiation. And then just take your usual derivative of that now single variable function. So again, notation, there's the sort of Leibniz-like notation, but heads up about that symbol. That's a new symbol. You got to make sure to, use that correct symbol. And then there's the Newton-like notation, which, in here and there, this one's actually really convenient too. They're both convenient in their moments. So that's how it's done and how you notate it. And then the process, and we went through some of these, I guess we went through all of these on this page last time, but the big idea is to step one, identify what your variable is, right? Then identify the expressions in what you're taking the derivative of that have that variable in it. And then identify and recognize as constants everything else that doesn't have any of that variable in it anyway. Right, so be a careful eye on what's your variable and what else are constants. And with the constants identified, you just kind of ignore them. Treat them like any other. Treat them like it's a 6, right? And then not much differentiations left over sometimes. And of course, the y derivative of y squared is just 2y, and we're done. Okay. All right. And then again, sometimes it looks weird. Sometimes it looks too good to be true. Here, x is our variable. So this has got variables in it, but this part up here, whoops, wrong color. This part up here is a constant, and we treat it as such with the, -1 and all that. Okay. Okay. So where we ended last time was trying to make geometric sense out of this, right? Again, I wrote down some formulas, but you can kind of write down any formulas you want. That doesn't mean it has to mean something. It certainly doesn't mean that it means what you wish it meant, right? So, okay, so what does this partial derivative mean? Again, I cannot emphasize enough. Y'all know I'm a big believer in making a conscious effort to always think about what kind of a picture are you looking at. If you're thinking graph when you're actually looking at a level set, you're going to be way off on everything, right? And et cetera. So when I say geometric interpretations, with that point in mind, let's start by thinking about, let's make a choice, and we're going to start with thinking about graphs. So in the graph context, what do partial derivatives look like? All right, so here we go. Here's an example of a graph of a function of two variables. Notice it's a surface. Right? We've got two input variables that are kind of down here, if you will. Graph means that the output variable is what we set the function equal to. That's the vertical axis. And that gives me a surface then, right? This equation gives me, in this case, a surface. And I want to compute the partial derivative. Now, I do have to say where I'm computing the partial derivative. They're different depending on where you look. So I'm going to look at the point AB. That means that the input values are AB. So said differently, in the XY plane, the point I'm looking at is AB. On the graph, there's a corresponding point up there, sure, right? But we think of it as we're taking the partial derivative here. Keep in mind, we're not actually here. That's a point on this construction that we use to visualize things. Where we actually are, right? This point AB is not on the graph. It's in the domain. Okie dokie. So here we go. Step one on a partial derivative is we fix all the other variables. That's just in general when you take a partial derivative. So what does it look like geometrically if we fix all the other variables? Well, the other variable is, well, there's only one other variable. It's just x. I'm going to fix x. So whatever the value of x is, in this case, a, I'm going to declare a to be a constant. So we are going to therefore not leave this plane. Right? That's the plane where x is equal to a. So in other words, this first step in the process of taking a partial derivative is to take a vertical cross section of our graph. That's just what this happens to look like in the graph context. Right? Vertical cross section. And now we had this, originally we had this whole surface, but as we are taking the cross section, this x equals a cross section, that gives us a just a curve now, the slice, if you will, of that graph. Let me pause for a second. How's everybody doing? Is everybody with me? Okay. All righty, taking that slice. By the way, very often it's confusing to think about, and you just have to think this through and make sure to get this straight. But fixing x makes a plane that's parallel to the y-axis, right? It means that it's allowing you to move in some sense in the y direction. And that just, I don't know, it seems a little, I don't want to say it seems wrong, but you can't just go by it's the x and so x. And then instinctively you might want to draw a plane parallel to the x-axis. And of course, that's wrong. Right, so make sure to always think it through what you're actually doing. Okay, next step. Take the derivative with respect to y. Well, what is a derivative? If we have a curve, which we do, derivative means look at the tangent line, right? And then we take the slope of that tangent line. Right? Again, just flashbacks to Calc 1. So that's what a partial derivative is. And this is the nice summary of it. You want to know what is a partial derivative with respect to y. In the graph context, you're going to look at the tangent line in the y direction. And keep in mind, we're going in the y direction because going in the y direction corresponds to x being a constant. Right? So we're going at, which by the way, good news, right? I mean, y direction, because y is the variable. That actually tracks. That makes sense. Right? That's what you would sort of expect. So we're going to look at the tangent line in the y direction. And then we take the slope of that tangent line. Yeah. Here's the really good news, of course. This is very familiar, right? We're accustomed to partial derivatives being slopes of tangent lines. That's nice, right? What we have to do here, the thing we have to remember and sort of focus on in this new context is, don't forget, now we have to make sure that we're actually looking at a graph before we use this interpretation, because this only works for graphs. And you don't have to be uptight about that in Calc 1, because in Calc 1, everything's a graph. But you do have to be careful about that now. The other sort of thing we have to adapt from the familiar, derivatives or slopes, is that don't forget there's actually a lot of tangent lines to this graph. There's a bunch of them, right? I mean, there's that one there, but there's other ones, and there's a whole tangent plane even, in which, of course, there's just countless tangent lines. right? So you cannot just say a partial derivative is the slope of the graph. Slope in which direction? There's a million directions you can go. It's the slope. Where'd it go? Yeah, here we go. In the y direction. Yeah. Okay, so now I have a suggested exercise for y'all, and that is to think through an analogous argument, draw the analogous pictures, right? And you'll be careful, try to document everything as if you're trying to explain it to a pen pal that you're writing to, right? I think it's a really good exercise. Think through how would you argue and explain what an x partial looks like in the graph setting. And here's what the answer is. It's exactly what you would think, a slope of the tangent line in the x direction. Exactly what you would think. But think through that argument. Everybody see what I'm suggesting? Okay, now, yeah, tragically, not everything is a graph. Tragically, sometimes the graph is inaccessible, and you'd say, well, I'm going to think about it in terms of the graph, instead, right? So take this, for example, and if you're looking at a function from R3 to R1, we've talked about this before, the graph would be in a 4-dimensional space, and we can't draw that, and we can't visualize that. So, all right, how do I visualize a function like this? Well, one option is to what I like to call, again, the literal picture, where you literally draw the domain, right? And you literally draw the target. And the action of the function that takes points from the domain and lands them in the target. All right, let's represent that action with an arrow. It's just very directly what the function fundamentally is. In this picture, what does a partial derivative look like? Well, it is kind of exactly what you would think. The partial derivative is the thing that is the relationship between the output change and the input change. Right, now we've got to follow the rules. Don't forget, when we're taking the partial with respect to y, that means that x is constant and z is constant. Right, both of those variables are constant. So from the point in question, we're only allowed to move in that direction, just in the y direction. So with the assumption that y is the only variable changing, you move a little bit in the y direction, that's going to make the function change, and the partial derivative is the relationship between those. Notice it's not a slope, right? So you got to be careful about that. Don't misinterpret because you're looking at the wrong kind of picture. Everybody on board? Yes.
What would a problem look like? I don't know that I fully understand what the partial derivative actually is here.
Well, yeah. So that's I totally get that, right? I mean, the satisfaction very often comes from, feeling like you know what something is very often is because I know what it is because I can see it, and this is unsatisfying in that way. Right, so that's, I can't fix that. That's in this picture. The best I can give you is the partial derivative. Well, it's a relationship between input changes and output changes, and that's just kind of what it is. It might be helpful then if to recognize that the source of your dissatisfaction is the lack of being able to point to it. It might help you be more satisfied with that lack, because that's just, there is no, I can't point to it. There is no pointing to it. Does that make sense? Yeah, and it is unsatisfying, and that's the nature of the beast, right? Yes.
Why are we able to set df over dy equal to like the other symbol that we have, like weird f over weird y, like that bottom equation df equals?
Oh, yeah, no, I hear you. Right. Okay, so good question. So you're wondering why can't I literally say, well, that's called DF, so let me just write that as DF.
Well, no,
right.
I'm wondering why we're allowed to set, because like you cautioned us earlier against
Yeah.
not using any of these symbols for one another, right? But
Yeah.
the equation at the bottom, like
Yeah.
essentially is DF over DY is
Yeah.
equal to.
Yeah. No, I hear you, because there's this temptation to want to do that. Right. So anyway, let me just directly answer your question. When I write this down, it looks like a fraction, but it's actually not that, but also kind of that, and also more than that. This thing is not just the ratio between however much F changes and however much Y changed. This is a statement of, hey, by the way, there's a specific scenario going on here. The specific scenario is that X and Z are constants, and Y is changing, right? So that's what this variable, this notation here encodes, is that not just that Y is changing and F is changing, but also that X and Z are constants. And with that noted, then I can say, then it's just okay, all right, well, look, with that assumed, yeah, Y can change. Now, when I say, yeah, Y changed, I don't have to recognize that, I'm not writing down a part. This is not a partial derivative right here. This is just a Y changed. How much did it change? I'm calling it dy. It's a differential, right? And then I can ask, how much does F change? Again, that's just a differential. And I've already laid the groundwork that X and Z are constant in relating them by way of the partial derivative. So I don't know if that's satisfying, but it might help to take the point of view of you really shouldn't think of this as being a fraction. We draw it as a fraction because in certain ways it behaves like a fraction, but ultimately it's much more than a fraction. And we have to use the notation appropriate to the fact that it's not just a fraction.
Yeah.
Is that at all satisfying?
I don't think so. But
Okay. All right. Okay. You can come to office hours. We can talk about it more then.
Yeah.
Yeah. Yes.
Is dy equivalent to just like delta y here? Or not?
Yeah, kind of. Yeah. The difference between a D and a delta. So D, it's more interesting when you talk about output values. So D says DF does not refer to how much the function actually changes. DF refers to our linear estimate, based on just looking at what's happening very, very nearby, assuming that, just understanding, linear approximation, if you will, and we're actually going to talk about that in more detail later, but assuming that everything is kind of nice and flat near there, what would be our estimate of how much F changes? If you were to write delta F, that would say how much did F literally change? Yeah. So it's the difference between an estimate versus an actual. Is that cool? Yeah. Okay. All right. Yes.
So would you say, like, as an example, like if the partial derivative is like 5, you would say like for every little bit that you move in the y direction when you're holding x and z constant, you expect like the output to change like 5 times as much?
About 5 times as much. That's exactly right. Yeah. So just if this, oh gosh, stylus, if this were a 5, then yeah, exactly as you said, whatever this is going to be about 5 times as much. Yep, totally. All right. Okay, so my point to this picture is notice it's not a slope. And notice how different we have to, and the interpretation is. In fact, I would even say our geometric interpretation of the partial derivative here, it's not even really very geometric, which I think is what you weren't happy about. It's not that geometric in this. And again, so wish it weren't so, but it is,
When you said this helpful too, just like.
Yeah.
Examples.
Yeah. Good. Okay. All right, let's look at on the level set context. So here I've drawn a bunch of level sets, which it's going to mess up the picture if I leave them highlighted. But what does a partial derivative look like in this setting? Okay, well, let's start with partial derivative with respect to x and partial with respect to x means I'm moving in the x direction. It means that y is constant, and so y is fixed. And based on the picture, how much is f changing as I move as described? And I would argue it's changing a lot really fast. Check it out. I went up 200 feet over a mere very short little distance on the map there. So that's a lot of change in the function per unit, how far you moved in the x direction. So a large partial, because in that direction the level set lines are close together. Okay, now by comparison, suppose that we were looking at partial with respect to y. That would mean that we're moving in the y direction. That would mean that x is constant. And as I do this, as I move in that direction, how much, how fast is f changing? Well, look, it takes me that long. It takes me quite a bit longer distance to move up that same amount. For the function, increases by, I'm going to say again, 200 feet, two levels. Pretend like this is contour lines on an altitude map, right? Takes a lot more distance to gain that same amount of altitude. That's just not as much change per unit distance. And so I argue smaller partial. Yes.
So is it just basically the same way like a topographical
Yeah.
map works?
Yeah, that's absolutely right. So you just partial derivative is going to represent how steep is the mountain in that direction with slope of the tangent line if you were looking at the graph, right? And that's a steep climb, and that's a much less steep climb. Yeah. Okay, so again, big thing to notice about this, the interpretation of the partial derivative, neither one is a slope on this picture. It's definitely not, neither one gives you that slope of that tangent line to that level curve, right? Neither one, here, let me do it like this. That does not tell you the slope of that line. That does not tell you the slope of that line. It's not what it is, because this isn't a graph. And, and trying to make sense out of either one of these as being that slope is, again, that's just a mismatch. It's, that's the wrong tool for the context. Everybody good? Okay. All right. So we're going to try to extend all of this now to kind of a more general case. In fact, let me go back a few pages here and remind you that I gave you this warning that partial derivatives really not the best way to think about derivatives of multivariable functions. And again, they have their uses, and the interpretations we just saw are kind of neat, I guess, or something. But there is a much more general and powerful and really appropriate way to think about multivariable derivatives. And the first step we're going to take in that direction, whoops, I just was there, is linear approximations. So y'all remember linear approximations from single variable calculus, and there it is. Familiar, right? Everybody's seen that before? Okay, so okay. Why is that the linear approximation? Different ways to think about this. A lot of people take the point of view of, well, first draw the tangent line and then try to figure out the equation of the tangent line and then interpret that as a function. I personally think that that's kind of putting the cart before the horse. I think this is the linear approximation because this is the unique first degree polynomial that agrees in value and derivative with the function that we're trying to approximate. This, in other words, this is the function that mimics f as best as possible, compared to, given that you're looking at a degree 1 polynomial. So in other words, among lines, this mimics f as best you can. So how do I, how would I confirm that this is the linear approximation to f? Well, I would observe that it's got the exact same value as f, and it's got this exact same derivative as f. And these are just very quick little calculations to confirm, right? So L of a, if I were to plug in a for x, well, then check it out. I've got, a minus a there. This whole term goes away, and sure enough, L of a is f. If I take the derivative, now don't forget when you're taking a derivative, a is a constant. So f prime of a, whatever number that is, it's a constant for the purposes of the derivative, because this is not f prime of x, this is f prime of a, right? And well, the only term here that has any x's in it is that term right there. And so what is, what do you get when you take the derivative of L? Well, you get, that constant, namely f prime of a. So I don't have to draw graphs at all. I don't have to assume that I have, one could argue that maybe we should be a little suspicious of our own intuition for what a tangent line is. I don't know if y'all ever worried about that, but not every curve has a tangent line. What do you do then? Right? But I think it's real easy to argue algebraically that finding the unique first order polynomial, same value, same derivative. So once you confirm these facts, that's a linear approximation. Okay, so with that point of view in mind, what if I have a function that has several input variables? And I'm going to take basically the same approach. I'm going to write down what I think the answer is. I don't even really have to justify where I got that from, but I'm going to say, I think this is the answer. And now to make that legitimate, I have to confirm that it's got the same value as f. And that it's got, okay, well, now there's multiple partial derivatives. So I've got to make sure it's got all the same several partial derivatives as the function f. So a couple of calculations and we win. I don't have to make any argument about tangent and geometrically, what does this look like? And what defines a tangent plane? Oh my gosh, that's hard. Especially when n is large, right? What if n is 7? Now you can't even dream about drawing a tangent plane. But we can always do this kind of thing. Okay, now again, how do you confirm this? And I want everybody to do this. I think this is a good exercise. And that is, don't forget that these are constants. Right? All these partial derivatives are being evaluated at the whatever your base point A is. And plug in what is L of A, confirm that you get F of A. Take the appropriate, take all the different partials sort of one at a time and confirm that, sure enough, the partials of L are the partials of F. It's a lot like what we did up here. Okay. And good news, it works. So, so there's your linear approximation of a multivariable function. Notice it's got sort of a bunch of different terms. It's got sort of an x1 term, if you will. And then it's got an xn term. And all of those different terms pretty much are just rip-offs of the original sort of, there was only sort of one non-constant term for the single variable case. So it's totally just a sort of copycat rip-off of the single variable. Yeah.
What is the vertical line? Like the,
Oh, yeah. So he's asking about this notation here. That is just notation saying evaluated at the point A. Sometimes I just think it's kind of clunky when you have parentheses with another parentheses next to it and well, what's going on there. And so if I had written partial of f with respect to xn parentheses a, and then right next to that is parentheses xn minus an, I just think it looks weird. So this is an alternative way of saying evaluated at that point.
okay.
Yep.
So it's like
It means the same thing that this does.
okay.
Yep. Oh. Okay. Okay, so y'all are going to check the algebra that I just claimed there, but this does work. That is the answer. And now I want to draw your attention to what this looks like. And I claim that if you think about it, it actually looks like a dot product because we've got a bunch of terms, excuse me, a bunch of factors there that are being multiplied by a bunch of other factors that look like that. I mean, structurally, it looks like a dot product. The right-hand side of that dot product are literally the coordinates of this vector, the x vector minus the a vector. It's your displacement vector. It's your input differential, you might call it. So where we are then, this clearly very important expression that's, doing most of the heavy lifting in our linear approximation is a dot product, supernatural construction dot product of something with our input differential. Well, that's a supernatural, extremely natural. I don't mean supernatural, like there's no ghosts here, right? But it's an extremely natural object in relation to what we're doing here. So this other thing here, whose coordinates are those partial derivatives, that thing must be interesting because it connects in a natural way to a natural thing in an important construction. I mean, why it's interesting? I don't know anything interesting about it other than the fact that it connects in this way, but I'm now highly suspicious that this vector that participates in this formula like that must be pretty cool. And by the way, that is going to bear out over time. So for the moment, I'm just going to make a definition and say, due to my suspicion of it being interesting, this is worth studying. Call it the gradient. That's the name. And then we're just going to kind of keep our eye on that going forward as likely to be interesting. Yeah.
Do you think of the gradient as like I guess, if I remember correctly, like a Jacobian?
Absolutely. Yeah, we're going to get to that. Yeah, it is. Absolutely. That's, in fact, I think it's on the next page of the notes. Yeah. Yes. Okay. So let's see an example. Here's our streamlined linear approximation formula. And let's apply that to this function at that point. Well, I'm going to need to compute this thing, this gradient thing. So I'm going to have to take all the different partial derivatives of my function. And there they are. That's just partial derivatives, right? Y'all can think through the algebra on that. And then don't forget to plug in the point, at the point A. So we're going to take these values, plug them in. That gives us what the gradient is at that actual point. And so the gradient vector, 2, 4, goes right there. You can see x minus a right here. There's x minus a. Don't forget a is 1, 2. And yeah, I guess I'd also need to compute f of a. Well, that's just, again, plug in the point into plug that into there. And boom, there you go. Plug and chug. Everybody happy? Okay. All right. So what if we had not just a multivariable function? What if we had multiple output variables? In other words, a vector valued multivariable function. Now, look what I've done over here in this example. I wrote out a formula that was kind of a coordinate-wise formula, and then I compactified that later, noticing that this vector thing was going to be important. If I were to write out a coordinate-wise answer to what how to do linear approximations here, I would have, oh my God, so many terms. I don't want to write out all those terms. And so I'm going to start with the compactified formula. And as it turns out, and again, y'all are going to confirm all this with direct calculation, but this matrix is going to be the thing. It's going to play the role kind of like the gradient did in the previous formula. It's a matrix of partial derivatives. The rows represent, each row, I'll say, represents one of the output components that you're taking a partial derivative of. Each column represents an input variable that you're taking a partial with respect to. So that's the organizing principle here. Right, and by the way, you gotta be really careful to get that straight. It's so easy to accidentally transpose that and do it the sort of, oh, I got my rows were my columns were my rows. Super easy to mess that up. So do be careful. It will give you wrong answers if you sort of transpose that. Okay. So that said, I claim that this, again, you would kind of expect it, value plus derivative times displacement, right? It looks just like the linear estimate formula from single variable. This would be our sort of guess as to, maybe this would be a linear approximation, and it totally bears out. So this has the correct value. And for every I and j, it has all the appropriate partial derivatives. Now, again, there's a bunch of terms to write down there, and I think this is a healthy exercise for y'all to do on your own. So what I'm going to ask you to do, in other words, is multiply this out in components, right? So you're going to have to write this in components. You're going to have to expand that out as, what it is up here, and laboriously multiply out, right, this product, and then start taking the partials, remembering, of course, that everything in here is a constant. Start taking the partials and confirm that, yeah, sure enough, it gives you exactly what you need. Okay, yep. Now here, again, example. So here we have a vector valued multivariable function, right? So 2 input variables, 3 output variables. And for that input point, 1, 2, what would be the linear how would I make a linear estimate of this function? All right, well, it's this. So I'm going to have to plug in, to that. First thing I'm going to figure out is, what is this DF matrix? Don't forget the DF matrix is all of that up there. And okay, so first column is the partials with respect to x. Put a little x down there. And then the second column, this is the partials with respect to y. It doesn't look like a y. There we go. So now that's, for each one of those columns, you got 3 partial derivatives to compute. So again, make sure you can do that, right? It's world's easiest derivatives, right? But nevertheless, make sure that you're proficient with that. That gives me my DF matrix. I'm interested in what's going on at that point 1, 2. So this becomes that, just arithmetic. And there you go. There's your DF. And you've, of course, also got to take A and plug it in to get the value of the function. Right? We already got the matrix there. And then that gets multiplied by x minus A. And there you go. There's our linear estimate. And if you want to multiply that out, you can. I'm going to tell you, I think in most cases, it's more convenient not to multiply it out. Just leave it in this form where you can see the sort of the components that go into it. I think this is really better. But again, if you want to multiply it out, knock yourself out. Everybody okay? Okay. Okay. A couple of observations to make. Somebody asked about this minute ago. But this DF matrix, again, it's notation. For the moment, it's just notate. It's how you assemble. Let me go back up to here. It's how you assemble all the individual partial derivatives that eventually I'm going to need to confirm are, participate in the linear approximation the way they're supposed to. So it's just notation for the moment. That said, it's worth noting now a couple of things. The rows are these previously observed things, namely the gradients. Each row is a gradient of a component function. How about that? Just direct observation. Each column is a partial derivative of the vector value of the function. That's pretty neato as well. And also, I'm just going to observe that this is actually linear. DF is actually linear. And this goes back to something I kind of glossed over earlier. Let me go back to where we first defined linear approximations. Technically, the linear approximation is not linear, right? I mean, it's not. Y'all remember linearity? Among the many needs, many features of a linear function, 0 goes to 0. This clearly doesn't. Plug in x equals 0, you don't get 0. Right? So the linear approximation is not linear. It's super awkward. It's this other thing. It's called affine. Affine means linear plus a constant, pretty much. Right? But this is not linear. And then likewise, going down here to where we write, this multivariable linear approximation, that thing there, this is not linear. The linear approximation is not linear. It's weird. This is, though. Okay. So that's why they call it a linear approximation, is because the thing doing the heavy lifting is actually linear. Okay. Oh yeah, I got ahead of myself. Okay, so tangent lines, tangent planes. What are we going to do about that? Reminder from single variable calculus. Once you know the linear approximation, right, it's a pretty easy case to make that the graph of the linear approximation should track the graph of the function itself. Right, so we got two graphs there. Point being, if L is approximating F, then the graph of L and the graph of F should relate correspondingly. So now again, I like to do this kind of backwards from the way a lot of single variable calculus classes will draw the tangent line first, and then use the equation of the tangent line to motivate the linear approximation. I think it holds better water if you start with the linear approximation and then describe its graph as a tangent line. Okay, so that also sets us up very nicely then for the multivariable version. We know the linear, wrong color. We know the linear approximation, right? We can talk about the graph of that linear approximation. Well, gosh, that graph is, let's see here. We have Z is the output variable. We have two variables, X and Y are the input. So the graph is going to be a plane in space, whereas the graph of the original function is a surface that, again, I think is reasonable to argue this plane should be sort of tracking. So this is the definition of the tangent plane. Totally in analogy with what we did in what should have been done in single variable. Okay. All right, now we've got some awkward formalities to worry about. I don't want to spend a lot of time on this because this is not really the focus of the course, but it's important that the following things be said so that you're aware that there are uncomfortable issues There are some scary things out there. And in this class, we're going to mostly stay on the trail. And if you stay on the trail, then there's no scary monsters. But I want y'all to know there are scary monsters if you step off the trail, right? So here's the thing. We wrote down this thing called L. We called it the linear approximation, but you will notice I put a disclaimer way back here at the beginning. If there is a linear approximation in the first place. So I was assuming that there is such a thing. So it's a very thorny question to ask, is there actually a linear approximation in the first place? And so I'm going to try to persuade you that sometimes there might not be by this example. Check out this function. Now that's a weird function. It's a super weird function. This is the tip of the iceberg, by the way. There is much weirder functions than this out there, but it's a perfectly legal function that's defined to be 1 on the x, above the x and y axes, right? And then it's defined to be 0 sort of everywhere else. So it's, kind of over here, it's 0, and then over here, it's 0, etc. Right? So it's 0 everywhere, except for on the axes. Weird, but legal. Now that function, if you do the linear approximation, the linear approximation is based on what's the value at the origin? Well, 1. What are the partial derivatives? No problem. The partial derivatives are both 0. And so my linear approximation is just the constant value 1. My linear approximation, my resulting tangent plane would be just a plane at height 1 sitting above the xy plane. Is that a tangent plane? Oh, no. All right. Does this orange thing do a good job of approximating the function? Not even close. It's horrible. It's way off. Right? And the blame is on the function. This function is a messed up function. This function is not good enough to have a linear approximation. So, look, mathematicians worry a lot about situations like this where, we write down certain formulas with, simple cases in mind. And we're constantly scared that, okay, well, yeah, but that works in the simple cases, but might there be some weird situation out there? If I just blindly adhere to this formula, will I inadvertently write down absolute garbage? Right? If you were to cite this as being a good approximation of this function f, you're dramatically off base. Okay, so how are we gonna deal with this? So one thing you can do is you can ask, what's the error? The difference between the actual value and your linear estimate of the value, and ask, how about if I just require that the error go to 0? Right? If the error is approaching 0, surely that's a good approximation. But I want to point out that no, that's actually not a very good approximation. Take, for example, this function, whose graph looks like that. And let me ask, is this a good linear estimate? Does the blue line track the green line? Well, no. Laughably, no. Of course not. It's way off. It's not even pointing in the right direction. And yet, the error, right? If you look at the error, the error is that minus that. There's the error. The error is approaching 0 as you approach the origin. So that makes me not like this idea of, well, just make sure the error goes to 0. The error can go to 0 for even bad estimates. Okay, so that was our first attempt. What works better is this thing called relative error. So relative error says, okay, look at the error, but see how that compares to how much your displacement is away from your base point. And so we're not going to ask, does the error approach 0? We're going to ask, does the relative error approach 0? In other words, even after you divide by this thing approaching 0, does the fraction itself still approach zero because the error is going to zero so fast? And you can see here, we'll revisit this same example we looked at a second ago. This function, this candidate, linear approximation, right? Laughably bad candidate. The error approaches zero, but the relative error, let's see here. You try to use the same colors. There's the error. But when I divide by x minus a, right? Purple divided by red there, you can look in the picture and persuade yourself that, yeah, sure, the error is getting small, but the displacement is getting small in some sense at kind of the same rate. And as a fraction, this fraction is not approaching zero. This is approaching 2. So this idea of looking at the relative error correctly distinguishes that this is not a good linear approximation. This is a good this has correctly rejected this bad candidate. Okay, so this is what we base the idea of differentiability on. And now there's a big formula down here, and this is a scary page, and so we're going to take this kind of cautious just a little bit at a time. But this is how we define differentiability, and it's in the book. We say that the function is differentiable, or said differently, that our linear approximation actually is a meaningful, good linear approximation if the relative error approaches zero. That's really all the definition says. Relative error approaches zero. Now, don't forget relative error is that. And then don't forget error is that it's the difference between the approximated value and the real value. And don't forget that your linear approximation itself is all of this, which I have to, of course, put some parentheses in here. So really all this is saying how much of the function, how much am I off in my approximation compared to how far did I move away from the base? It's all this is, it's relative error. And if your relative error approaches zero, then we say, okay, that's a good approximation. Okay, that's the formality. Oh, I went over time. I'm sorry. That's the definition, and we'll draw a line right here. There's a little bit more lingo here. It's not important. And call that a day. See y'all later. And don't forget, I have office hours in just a couple minutes. Zoom, of course, and maybe see you there. Have a good day.